Swayam Prabha. Digital India. Educated India.
We have the last paper of this session by Swayam Prabha, IIT Madras here. The title is Time Series Segmentation Using Topological Data Analysis.
Hello everyone, good afternoon. I am Shubham and I am working on the topic segmentation of time series using topological features. I am working under the guidance of Professor Raghunathan Rangaswamy, my mentor Lokesh, and with my colleague Jaswant Krishna. Okay, so first let's understand what is segmentation of time series and why is it important. So as we know, time series data is ubiquitous. It is encountered in a variety of fields, and many time series in the real world contain distinct modes or behaviors. So as we can see in this plot, this time series can be divided into three parts where each part corresponds to a distinct characteristics. So segmentation, which is also called a change point detection, tries to identify the boundaries between these different modes. So this is the goal of segmentation. So for example, we have an EEG recording and we are trying to find the boundaries between different phases of sleep or brain activity. There are many such examples in the industrial domain, biomedical domain. So why is segmentation important? It is important because when we divide the time series into parts, it's easier for a human to interpret it. And it's also useful as a pre-processing step so that we can separate it into different parts before feeding it into a machine learning model or a data science algorithm. So segmentation is a well-established problem. It has been studied for the past few decades. Many algorithms have been developed for performing segmentation. So mathematically, this problem is stated as follows. Suppose we have n data points, where each xi is a d-dimensional vector. It could be a multivariate time series. And this time series comprises of k different processes. So the goal of segmentation, stated mathematically, is to identify these k boundaries or these k-1 boundaries, which separate the different processes. So there are two classes of methods, the conventional ones and the more recent deep learning methods. The conventional methods construct piecewise functions or distributions to approximate the data. So in the jth window, we could have function f of theta j, but the functional form or the parametric form of f needs to be known beforehand. So f could either be fixed as a polynomial model or an AR model, or it could be a kind of distribution. But these assumptions may not generalize well to different domains. These could be specific to a particular domain. But the advantage of these methods is that they incur a low computational cost. On the other hand, we have deep learning techniques which can learn more complex features from time series. So they learn certain embeddings for each window in the time series. And based on the similarity of the embeddings, they can identify the change points. Here, the model structure is not decided beforehand. So these methods are able to learn more complex representations, but there's always a trade-off. So deep learning methods require a lot of data to train and they incur a high computational cost. So is there a way to incorporate the desirable points from both these methods and come up with a new algorithm for segmentation, right? The method should be able to capture complex features, but it should not have a very high computational cost. So topological data analysis, which is a new upcoming area in data science, captures the shape of data. And this shape can be used to train the model based on features. So can we use these topological features to come up with such a segmentation algorithm? That's what we are trying to investigate in our work. So let's take a detour and understand briefly about topological data analysis. So topology deals, as we all know, it deals with the shapes of objects. Computational topology, which is a recent field, it tries to capture the shapes of objects using discrete points drawn from it. So in real world data sets, we don't know the actual equation of the surface. We can only draw discrete points from it. And using these discrete points, is there a way to infer the shape of the data? So the basic idea is to construct a neighborhood around every point and take the union of all these neighborhoods or these balls, and the structure of this union in some way corresponds to the topology or the shape of the surface which generated the data. We'll look at some more details. Suppose we have a set of points. We construct an epsilon neighborhood for every point. If the epsilon neighborhoods of 2 points intersect, then we join them with an edge. And this way we can construct a graph with the points as vertices, and we have edges between the points if the neighborhoods intersect. So we have a particular graph for a given value of epsilon. Now we can take different values of epsilon. We can start with small values and increase the value of epsilon gradually. And at every point, we get a different graph. So this multi-scale feature, this multi-scale representation, is what captures the shape of the data. So this is one of the pioneering works which develops algorithms for capturing the features of data. So different topological features, like for example, connected components or cycles, can be captured using this graph representation. So as we saw, particular feature might be created at a certain value of epsilon, and it may be destroyed at higher values. So this is what is represented in a persistence diagram. So we have the birth time on the x-axis and the death time on the y-axis, and we represent the features, the shapes, the different shapes in this data set, in this persistence diagram. The features which are far away from the diagonal last for a longer duration over a wide range of epsilons. They can be considered more significant. So coming back to time series, how do we apply these techniques from topological data analysis to time series, right? Let's say we have a multivariate time series. We could think of the unordered set of points x1 to xn as a representative of the surface which generates the time series. So these points in some way represent the trajectory of the time series, and this could be considered as the point cloud. And this point cloud is given as an input to topological data analysis, the TDA pipeline. And once we have these persistence diagrams or these features, we have learned a representation of the time series, which can be used for downstream tasks. So in many existing works, this kind of an approach has been successfully applied to time series data from different kinds of domains. In our investigation, we used a human activity recognition data set from this source. It includes 3D accelerometer data recorded while human subjects are performing different physical activities. And we see that the shapes and the persistence diagrams are very distinct for different kinds of activities. For example, for running, this is how the point cloud looks and the persistence diagram looks. Whereas if we take, say, another activity like walking, the shape is very distinct. It's different. And this shape, which is summarized in the persistence diagram, helps us to distinguish between different activities. So let's see how we can apply these features for performing time series segmentation. So I won't go into the mathematical details here. So given any two persistence diagrams or any two features, we need to quantify whether they are similar or not, right? I mean, this is applicable to any machine learning task. So there's a metric called Wasserstein distance, which quantifies the similarity or the distance between two persistence diagrams. And this gives us a notion of whether 2 point clouds or the topology of 2 point clouds is similar or not. So this is how the pipeline looks like. So we have an input time series, a multivariate time series. We get a point cloud embedding, compute the persistence diagram, and use a distance metric to quantify whether these two time series are similar or not. Now, suppose we have a time series and we consider multiple windows across the time series. We divide the time series into windows. The window length could be either chosen empirically or based on domain knowledge. And for every window, we apply this pipeline described in the previous slide. We get a representation, feature representation for every window. Once we have such a representation, we can find the pairwise similarity between these features. And this is what we observe from one of the data sets. So the light colored regions along the diagonal of the matrix correspond to the true segments or the ground truth. We see that they have a very low density or a low value of the distance, whereas the off diagonal blocks are much brighter. The distances in those blocks are much higher. So we can also visualize this as TSNE plots. So there are three different activities or three different segments, and they are clearly clustered as you can see from the TSNE plots. So how do we exploit these representations to come up with the right boundaries or the right change points, right? So the broad outline of the algorithm we used. Suppose we have an input block, say from index 1 to index 2. We compute the density or the average distance over the block. We split the block into smaller blocks if the density is greater than a threshold. We continue this recursively until we get blocks which have a low enough density. This is the broad approach that we used. The results, the preliminary results at least, look promising because in the top diagram you can see the true change points or the ground truth. And at the bottom one you can see the computed change points which are computed by our algorithm. So at least visually the change points seem to correspond to the true change point, but we need to use metrics and further quantify the quality of our segmentation. So to conclude, we are attempting to connect the emerging area of topological data analysis to the existing segmentation techniques. We're trying to come up with a novel segmentation algorithm using the pairwise similarity of topological features. We hope that it will be able to address some of the drawbacks of the existing algorithms. In the future, we plan to test our algorithm on many data sets, check whether it's robust and it has some of the desirable properties that we expect. So thank you.
Okay, thank you. Time for questions. Yes, please. Over there. Yes. Ah, sorry. First.
Thanks for your talk. So I was wondering, the data that you're showing is primarily for static purposes. So I was wondering if there's dynamic data and there's transients between, let's say you want to go from a model to another model in an adaptive sense.
So you mean that there are no sharp change points?
There is some transients in between. Yeah, there's clear-cut sharp boundaries. Right. So and what happens? I mean, how do you deal with that? Is there any thought? Are there any thoughts on that?
So the topological features will vary slightly. They won't change suddenly, but we can come up with a technique to address those kinds of data sets. You can look into that. Sure. Thank you.
So this topological data analysis, have you looked at in the form of explainability to the deep neural networks, because they seem to be having link? Any comments on that? Have you looked at it?
We haven't looked at it from the angle of explainability. We are considering more the perspective of low computational cost compared to neural networks, or being more robust compared to neural networks. You can look at explainability also. Sure.
Okay, the last question.
So thank you for the talk. Just wanted to know that when we are constructing a graph, so are we doing it on the basis of the smoothness assumption, or what methodology are we particularly following?
So we don't have smoothness assumptions. We have a set of points and we construct some epsilon neighborhoods. If the neighborhoods of 2 points intersect, then we have an L between them. we keep on increasing epsilon and then we get a series of graphs.
Okay, so basically it's a distance-based approach in a
Right.
Okay. Okay. Thank you.
If you have questions, yes.
Thanks, very nice talk. I would like to understand whether you've explored, a simple clustering and whether these data points cluster far apart from each other and try to use the distance metric, rather than trying out these advanced techniques.
So what features would you use for clustering? What kind of features?
You have multi-dimensional data, right? So
Right.
take this multi-dimensional data and understand the topology,
Okay.
and then try to measure the distance between the two topologies. So rather you can try to do the clustering and see. Did you attempt that?
No. So you mean instead of constructing new features, we can just use the original data and cluster them. Cluster them.
Yeah.
We could try that.
Thanks.
Well, that's thanks to the speaker, Mr. Kashapi.
Thank you.
Thank you very much. And thank you for your active participation for all the speakers and audiences. Thank you. Bye.